Lab 6, Magnetic Molasses by Caitlin Schmidt. Well, for the introduction, the objective of this lab was to investigate magnetic induction and eddy currents by analyzing the interaction of a falling bar magnet with a falling tube. And the method was that the observed fall time of the magnet compared to the results from the computational model, and the results for the experimental were 1.25 seconds, and the computational results was 0.973 seconds. Now for the key principles of physics for this lab, so it's the Biot-Savart law, which is a magnetic field generated by a constant electric current, and this is specifically for a point charge. Faraday's law, which is the electromotive force, is produced when magnetic flux or field changes over time, and the negative sign is Lenz's law. And Newton's second and third law, the force is equal to mass times acceleration. For every action, there is an equal and opposite reaction. Time for the observed model, and there is a picture of us doing it right there. The initial conditions were the bar magnet and the stopwatch, and the system was the bar magnet and the aluminum tube, and surroundings was everything else in the universe. So now it's time for collecting the data and calculations. So the bar magnet mass was 0.026 kilograms, and the mu of the magnet was 1.477 amperes to the meter squared. And the aluminum tube, the length of it was 0.3 meters, the width was 0.0065 meters, the inner radius was 0.024 meters, and the outer radius was 0.005, and the average time was 1.235 seconds, and then there's just a table of the times right there. Now, the computational model was made using GlowScript, and I have a link to my code in the abstract, but these are all the initial conditions. And here is the rest of the computational model, and the arrows are pointing to the most important equations, which is the B field calculation, the denominator calculation, the magnetic field of the ring, and that was all. Here are the results that came from the code, which is the plot, and also how the magnet looked when I was falling. Comparison and errors, the model discrepancies were obviously the observed time versus the computational time. The computational is more accurate, but yeah. And the potential errors are that electronic/magnetic devices could have affected the forces that were in the area, and friction against the sides of the tubes were not calculated, and also human error with the stopwatch. And the assumptions were that the bar magnet acts as a magnetic dipole, so we can apply the Biot-Savart law, and to neglect a resistance and only acknowledge magnetic and gravitational forces. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? Because of Ohm's law, the induced current in the aluminum tube would be much greater. It could create a greater magnetic force on the magnet and counteract with gravitational force, which would prevent it from falling. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current in the aluminum tube would be less because the holes would disrupt the current and the magnet would fall through much faster. Thank you for listening. I hope you have a great day.